Hey guys, we're back today and we're on Unit 7, Lesson 8. And today we're going to be dealing with another day of log word problems. This time we're going to be dealing with growth and decay type problems. So basically, many natural phenomena have been found to follow the law that an amount A varies with time according to the function A of t equals A sub 0 e to the kt. And we call this the exponential law or the law of uninhibited growth. Okay, so you may see this in future classes. Last year in your Algebra 2 trig course, you saw this function written as APERT. Okay, it's really your APERT formula. So even though it's fancy looking, it still just means the same thing. A of t is our final amount. A sub 0 is really the P. It's your initial amount. E is E, which is 2.718. It's our number. K is the rate of change as a decimal, and T is time. Now, the only reason I don't always, resort to using our APERT formula is as we move up in classes, as we take higher levels of math, you're going to see a lot of different symbols and notation. And I think it's important for you to understand how to use this, different notation and not be too afraid of it. So when we see that A sub 0, it really means the amount at time 0. That's all. We can easily determine when something is undergoing growth or decay just by looking at its graph, right? So if we see something going up, that's growth. That means our K value is greater than 0. And when we have decay, that means our K value is less than 0. Examples of growth in like science type of problems, which is what we're going to be dealing with today, cell division, fruit flies, amoebas, anything with that, like something of that nature. And then our decay type problems today will be involving radioactive material and half-life. Okay, so today, we are going to be dealing with sciencey types of problems instead of our business types of problems. When we do these types of problems, it's really important that you really, you read the question. They're a little bit more involved than the money problems. But I happen to be a very big fan of these types of problems. I really do enjoy them. So we have a colony of bacteria, and it grows according to the law of uninhibited growth, according to the function n of t equals 100 e to the 0.045t, where n is measured in grams and t is measured in days. And note, this is a typical Algebra 2 question here. Determine the initial amount of material. There's no trick to this. This is really just asking you, do you understand how to look at the formula, right? So I have n of t equals 100 e to the 0.045t. The initial amount is going to be the number in front of the e. We have 100 grams of bacteria. What is the growth rate of the bacteria? So I want to write this as a percent and a decimal. Well, looking at our formula, our rate is the K value, which is up here. So as a decimal, it's 0.045. And as a percent, remember, we moved that 2 places, it's 4.5%. Okay. So it's good just to understand how these things work together. What is the population after 5 days? Okay. So basically, what we're finding, if we were using function notation, we want to know n of 5, right? We want to know how much we're going to have after 5 days. So we're plugging 5 in for t. This is a simple plug-in. 100. We're going to use that second ln key. E, it's going to put that little raised to for you. 0.045 times 5. Hopefully I did that right. 125.232 grams. Okay, so that simple plug-in. How long will it take for the population to reach 140 grams? Okay, so now we're starting with 100. And we want to know how long it's going to take to reach 140. So we're going to isolate. A number equal to a number. So we're going to ln both sides. Just like yesterday, if you see that you're just going to bring that down in front, that's fine. I know my ln of e is going to equal 1. I don't cancel it out until I have it written. And then to solve for t, we're going to divide by 0.045. So ln of 1.4 divided by 0.045, 7.477 days. Okay, so these problems are fairly simple. Every once in a while, things might get a little tricky, but for the most part, they're straightforward and easy. We have a colony of bacteria increases according to the law of uninhibited growth. Okay, so that's important. If the number of bacteria doubles in 3 hours, how long will it take for the size of the colony to triple? Okay, difference in this problem, they didn't give you an equation to start with. Okay. So you have to kind of know. So I have my law of uninhibited growth. And if you like to use it in a PERT, that's fine. That's fine. But I kind of would like you to start going with the fancier notation. If the number of bacteria doubles, and how long will it take? Right. This is actually a two-part problem. I'm going to set up the second part first. How long will it take for the colony to triple? If you think about this, they're asking you how long it will take for the colony to triple. So if we were to solve that, we've got two variables up in that power. So in order to figure out what k is, we have to use the information they gave us here. The number of bacteria doubles. So this is a two-part question. We first have to find k. The number doubles. So I'm going to have 2 times whatever I start with, e to the k times 3. ln of 2 equals 3k ln of e. K is going to equal ln of 2 divided by 3. That's going to be some number. Okay, so if you evaluate that in your calculator, I have this decimal here. Notice I wrote down the entire decimal. So if you don't want to, you have to use it. Okay. When you're evaluating these things, you have to use the entire decimal in your evaluating. So if you just want to leave it over here written and only plug it in, that's okay. I usually just write it out because I don't ask you to do very many of these problems. So I have 0.23104. And this is the equation I'm actually solving now. How long is it going to take for this to triple? I'm not writing it down. I'm going to use it, but I didn't write it all the way down, all the way up. So I have t is going to equal ln of 3 divided by, and I'm just going to pull in my answer from above, the step above, and I get 4.755 hours. Okay, so notice once that whole decimal's in the calculator there, you can pull it in. That's why it shouldn't be so annoying. Let's get an example of a half-life. So remember, in chemistry, half-life is the amount of time it takes for half of the original amount to be remaining. So basically, an example of a type of problem you'd need to know would be the half-life of radium 226 is 1,600 years. What is its annual decay rate? So what does that mean we're looking for? We're looking for R. Okay. That's what we're not going to know. And basically, half-life means how long it takes for half of the original amount to be remaining. So if we're using our law of uninhibited growth, 1/2 a sub 0 equals a sub 0 e to the k, because really R is really k. I should have just used k. And the time is 1,600 years. That cancels. ln of 1/2 equals 1,600k ln of e. So k is going to equal ln of 1/2 divided by 1,600. You could write 0.5 if you want. That's no big deal. I want to do this on the actual calculator here. So I have ln of 1/2 divided by 1,600, and I get negative 0.000433217. I want to point out here, if you were doing this on a graphing calculator, because I know some of you are still using the graphing calculator, you would have gotten this number. It looks like that on your graphing calculator, and you have to recognize that as scientific notation. So you're going to move your decimal place 1, 2, 3, 4. So just be aware if you're doing it on the graphing calculator. I didn't realize that the iPad calculator would already convert it to you. So this is your, what did I do? One half divided by 1,600. Oh, it just rounded it differently at the end there. That's okay. It rounded it a little bit differently at the end. We're going to take the value from the iPad. Yeah, because it didn't go out as far as the graphing calculator did. Okay. The last type of example I want to look at today is like using this concept of half-life to help us. So and dealing with a multi-step problem. Basically, everyone should understand the concept of carbon dating. So every living thing contains carbon-14, and at death, it starts to decay without replacement. Okay, so they use this to kind of see how old something is. I don't necessarily understand how it works, but I know how to deal with the numbers. Like, how do they measure it? I don't know. Traces of burned wood, along with ancient stone tools and an archaeological dig in Chile, were found to contain approximately 1.6 per 7 of the original amount of carbon-14. If the half-life of carbon-14 is 5,600 years, approximately when was the tree cut and burned? Basically, it's asking you, right, how old is the tree? So we're really looking for, our answer is going to be some time, right? But again, this is going to be a two-step problem, similar to the first problem we did. So we need to figure out, in order to figure out um, how long it takes for there to be 1.67% or point, we have to find K. So we're going to use half-life to find K. Remember, half-life means how long it takes for half of the original amount to be remaining. In this case, it takes 5,600 years. So ln of 1/2 is equal to 5,600 K ln of E. Ln of E is 1. Our K, or our decay rate, is ln of 1/2 divided by 5,600. Negative 0.0001237763. Okay, so that's our K value. Notice it's negative. It's a decay rate. Now we're solving for T. ln of and I get 33,062.445. I know it sounds a little silly there, right? So, I mean, you can approximate to about 33,000 years ago, right? Because it says approximately when was the tree? However, if you don't want to round, if you want to give me the exact answer you get rounded to 3 decimal places, that is absolutely fine. Okay, so I hope you can appreciate all of the different types of things we did with our log functions and all the different types of situations we dealt with this year. You know, we're done with this unit. So now you could just do your homework and then we'll get ready for our test. Okay, thanks.